Hello everyone, welcome to my channel. My name is Yui. I'm excited to introduce my product, the LoRa button, a multifunctional wireless push button beyond LoRa technologies. Here's what we cover in this video. First, we go to a quick introduction. Next, we go to the system design. And then we talk about the measurement results and discuss them. And finally, we finish with a conclusion. The LoRa button is an IoT device I created to help you send information wirelessly using LoRa. Here's how it works. When you press the button, it sends a LoRaWAN packet. This packet is received by the LoRa gateway, which then forwards it to the Things Network cloud. The cloud supports protocols like MQTT and WebSocket, allowing you to connect your application to receive the data. In my case, I use the LoRa IoT platform to process and store the data. This platform offers many notification options, such as sending a alert via email or SMS. Even better, you can customize the message content. There are some reasons why I choose the LoRa technologies for my button. First, the LoRa ranks allow the button to work well over large areas. For example, it can be placed on a trash bin to notify cleaning start when it is full, or on a mailbox to alert you when there is a new letter. Second, it helps the button consume less power, which means you don't have to replace the battery frequently. Finally, it reduces coverage costs compared to other communication technologies like Wi-Fi or BLE. For the casing, I select the circular button that's readily available on the market. With a diameter of 46 mm and a height of 13 mm, it's compact and easy to use. The circular shape makes it ideal as an SOS button for the elderly in emergency. Additionally, it's compatible with the coil cell battery commonly used in small electronic devices. With this button case, I begin organizing the placement of the key components. In the beginning, we face a lot of challenges. Firstly, it's hard to find MCU integrated LoRa module. Secondly, with this button case, we have many limitations regarding the antenna and battery. Especially, the small dimensions make antenna design even more challenging. Next, choosing the battery holders meeting the criteria easy to replace and fit perfectly in this button case quite difficult. Finally, with the vibration feature, we have to deal with a high stack current and the electrical noise generated by the motor. The antenna I use in this device is a BFI antenna. I chose it because it is simple to design, offer high performance, and easy to adjust the frequency. The length of the microstrip is calculated by on the formula you can see on the left. In the middle is the BFI antenna I designed for the LoRa button. On the right is the radiation pattern of each antenna. Here's how the circuit is designed. I choose the rack 3172 as the main MCU, and temperature and humidity sensor connected to it via I2C protocol. To support low power application, I intentionally connected the button to the BA0 pin on the rack. It is the pin can wake up the MCU from deep sleep. The circuit is powered by an LDO regulator with a 3V output. I also added a battery measurement circuit to monitor battery level and know when it's time for the replacement. For notification, I use a vibration motor. However, if the motor runs normally, it uses a lot of energy. To resolve it, we implemented a PWM DAC to control the vibration level and reduce power consumption. For the firmware I developed for my device, there are three main steps. The first step is to initialize sensor and configure LoRaWAN. The second step is putting the MCU into sleep mode to save power. The final step runs only when the button is pressed. In this step, the MCU wakes up, collects sensor data, and measures the battery. Then it processes the data, so they're checking for any errors in sensor reading and verifying if the battery level is above the threshold. Then everything is right. The vibration motor starts to notify that all is well, and a packet is sent to LoRa 1 after that. On the other hand, if something is wrong, the LED blinks 3 times before sending a bucket to indicate an issue. It is just an example of firmware. You can develop new firmware on your own and upload that into the device through the Pokebin box. On the left side is the LoRa 1 is set to measure with nano-VNA, and on the right side is the result. By end result, we can see the antenna can work at a central frequency of 923 MHz with a bandwidth of 23 MHz and 13 MHz when the S11 value are minus 6 dB and minus 10 dB. To make sure the antenna can work exactly, we have to do more measure in the anechoic chamber. You can see the result on the right. After measurement, we can make sure that the antenna is right design and can work in real life. On the table is the current consumed in this phase, measured by IoT software. You can see the device spend a lot of energy on sensing, processing, sending, and vibration, with an average current about 100 mA. However, these phases in the device circle are short compared to the sleep time with the current 8 microampere, although the sleep time of the device depends on the user, but it's usually about 20 minutes or even more. So with low power consumption in sleep time, we can save much energy to help extend the battery life. With one battery concept, you can send about 500 packets with a battery life about 2 months. To extend maximum battery life, you can don't use a vibration feature in a custom firmware instance. With this config, you can use the LoRa button for 4 months or even more. Adding the PWM DAC really helps. Not only it is supported by the hardware, I also added a shock start technique in the firmware, so the high start current is completely gone. Looking at 2 waveforms, you can see that the PWM DAC really can control the vibration motor. As a result, the energy required for each notification has dropped significantly from 26 mWh to just 12 mWh. To measure the connection stability, I choose 2 locations. Firstly, in non-live side instance, I place a button on the ground floor with a distance to the LoRa gateway about 200 meters. With many obstacles, I use 2 buttons for this measurement. 1,500 packets are sent to have a loss ratio about 7%. Secondly, in the line upside instance, I place a button further away about 1 kilometer. I also use 2 buttons for this measurement. I sent 1,600 packets, and with this instant, there was a significant improvement in the loss ratio, which decreased to about 1%. To measure the communication range of the LoRa button, I use the TTN mapper to create a map. Here's how it works. Every packet the button sends is forwarded to the TTN mapper along with the location of your smartphone. So, to make the map accuracy, you need to keep the phone close to your device when sending the LoRa's packets. Every point in this map represents the packet sent, and the color of the point shows the signal strength. Red means the signal is the strongest, and the blues means it's the weakest. Looking at the map and the color of the points, we can see the LoRa 1 button has communication range of about 1 kilometer. This is the process I use to develop an IoT device. By following that, I can create a product with reliable communication with low power in a case available on the market. You can absolutely follow this process to build an IoT device on your own. Thanks for watching this video. I added a link in the description to another video showing some cool application you can try with my button. I hope you found the LoRa button interesting and enjoy hearing about its different uses. If you have any questions, feel free to leave it in the comment.